Welcome to Vcare Technical Institute.
Look at the unassuming, slightly dusty office phone sitting on your desk. Or, maybe that soft phone app minimized down in the corner of your screen.
Yeah, the one you probably completely ignore until it rings.
Right, exactly. You probably treat it like a water faucet. You pick it up, expect a dial tone, make your call, and just turn your brain off.
Yeah.
But today, we are going to shatter that illusion because that piece of plastic or that desktop widget, it isn't just a phone.
Far from it.
It is a vulnerable, hyperactive portal into a massive, heavily fortified IT nervous system.
And mapping out that nervous system really reveals some incredible engineering. Our mission for this deep dive relies on a fascinating stack of technical sources. We're diving into official training manuals from major telecom manufacturers like XRM and eStar.
Which are surprisingly dense, by the way.
Oh, absolutely. We're also dissecting real-world enterprise network curriculums, specifically looking at how things like IP addressing and quality of service completely dictate voice traffic. And we even pulled active job requirements for secure military communications just to see how routing logic works when national security is, well, quite literally on the line.
So we are going to crack open the black box of business telephony. We'll explore the strict, highly specific sequence engineers actually have to use to build these systems. We'll dissect how human speech is mathematically modeled into data, which is just wild.
It really is.
And we're going to uncover the economic mechanics of why network administrators live in a state of constant, completely justifiable paranoia about hackers. But before we get into the weeds of, trunks and dial plans, I want to pose a challenge.
Okay, let's hear it.
We are living in a world of Zoom, Microsoft Teams, Slack. I mean, almost everyone listening to this uses one of those on a daily basis. So why are enterprise companies still spending millions mapping out complex PBX architectures? Isn't a private branch exchange just like legacy tech hanging on for dear life?
I mean, it is very tempting to think of it that way. But a generic SaaS app simply cannot handle complex, specialized telecom environments.
Right.
Like, think about a hospital. When a hospital needs to integrate overhead paging systems with legacy analog emergency phones in the elevators, plus modern wireless iKey handsets for the nurses, a Slack huddle just doesn't cut it.
Yeah, that makes sense.
Yeah.
You can't just send a Teams invite to a physical elevator phone.
Exactly. You need a centralized brain that speaks multiple telecom protocols, interfaces with the public switch telephone network, the PSTN, and enforces highly granular routing logic. And that centralized brain is your PBX.
Okay, let's unpack this, because that requirement for, absolute control is incredibly apparent in the military sources we reviewed.
Oh, yeah. What's fascinating there is the physical manifestation of that control. If you look at the Indian Army's Southern Command, their communications require a closed-loop PBX so secure that they literally employ civil switch board operators. They call them CSBOs.
Right, because in that environment, you cannot simply pick up a handset and dial a neighboring unit directly.
No, absolutely not. You are forced to hit an exchange. You state your codes, and an operator physically or digitally switches your connection on a routing board.
It's like the old movies.
Sort of, yeah. And to do this, these operators have to master complex security protocols. They have to speak fluent Hindi and English just to verify and manage the endpoints. I mean, it is the ultimate air-gapped system.
Which is such a stark contrast to the modern enterprise environment, because today we rely heavily on hosted VoIP PBX systems.
Right.
These live almost entirely in the cloud, and they communicate using SIP. That's the Session Initiation Protocol.
Yeah, SIP is essentially the universal language that tells devices how to set up, manage, and tear down a digital phone call. It's what allows for this infinitely scalable architecture, bringing us features like Find Me, Follow Me.
Oh, I love that feature, where a call pings your desk phone, cascades to your cell phone, and then hunts down your home office before finally dropping into voicemail.
Exactly, and it's all entirely invisible to the person calling you. They just hear a ringing tone.
But making that routing magic happen requires a flawless underlying setup, which brings us to the core architecture, the holy trinity of extensions, trunks, and rules.
The building blocks.
Right. I was reviewing the Asterisk and Axtor and training manuals, and they hammer home a very rigid installation sequence. Like, an engineer must configure the system in this exact order. Step 1, extensions. Step 2, trunks. Step 3, the dial plan.
And they are very strict about that order. That rigid sequence forces the engineer to think exactly like the routing software.
Right, because logically, my non-engineer brain initially thought, well, if I'm setting up a new office, I want to connect the outside world first to ensure I actually have a dial tone from the phone company.
Sure, that makes intuitive sense to a human.
Yeah, so I would naturally start by building the trunks, the outbound connections. But if you think like the router, an inbound call needs a destination map immediately.
It's like trying to sort mail for a massive corporate department that hasn't even been assigned physical mailboxes yet.
Exactly. The PBX needs the internal grid mapped out before it even dares to accept a massive trunk line of incoming traffic.
Because the routing logic needs a verifiable internal database to check against in milliseconds. If a call comes through the trunk and the PBX looks for an extension that hasn't been registered yet, the packet drops, the call fails, and the system logs an error.
So you have to establish the internal endpoints first.
Always. Once those exist, then you configure the trunks your highways to the telecom providers. And finally, you lay down the dial plan, which serves as the connective tissue. It dictates the complex rules of how those internal endpoints are actually allowed to interact with the outside highways.
And the logic programmed into those trunks and dial plans is just wild. Let's talk about channel hunting. When the PBX needs to send a call out, you have, say, a CP trunk with 24 available channels, it doesn't just pick one at random, right?
No, not at all. It executes a hunting strategy. In the systems we reviewed, if an administrator configures the trunk with a lowercase r, the PBX performs a round-robin search, starting from the lowest available channel and working its way up.
But if they use an uppercase R,
It starts at the highest channel and hunts downward.
which is such a brilliant little detail.
It really is, because this prevents channel collisions if a provider is allocating inbound calls from the bottom up. It allows the local PBX to allocate outbound calls from the top down, so they never crash into each other in the middle.
Just brilliant traffic management. And then there's the pattern matching inside the dial plane itself. This was fascinating to me. The PBX isn't reading a phone number the way you or I do. It evaluates it as executable code using telecom regular expressions.
Yes, the syntax is almost like a programming language.
Right. In these environments, a Z stands for any digit 1 through 9, and X stands for any digit 0 through 9. And the system scans the digits as you physically dial them in real time.
Yeah, the moment the dial digits match an established pattern in the dial plan, the PBX instantly executes the corresponding rule. It doesn't wait for you to hit send.
The XRCOM manual provided a genius use case for this. Imagine your entire staff is accustomed to typing 00 to dial an international number.
Very common in Europe.
Yeah, but the IT department signs a new contract with a cheaper VoIP provider, and that new provider requires a 012 prefix to access their network. Retraining 300 employees to change how they dial the phone is just, that's a corporate nightmare.
And it would be a disaster. People would complain constantly.
So instead, the admin sets a pattern matching rule. The employee dials 00, the PBX intercepts it, seamlessly strips the 00 away, injects 012 in its place, and forces the call over the cheaper trunk.
And the employee has zero idea they are using a different provider.
Exactly. And the company saves thousands of dollars.
It is elegant manipulation on the fly. But executing that manipulation, stripping out digits, and rerouting SI traffic requires intensive computing power. And if we connect this to the bigger picture, all of that computing power and all of that clever pattern matching is utterly useless if the voice sounds like a garbled, robotic mess on the other end.
Yeah, that's the real nightmare.
That is the modern telecom engineer's biggest struggle, competing with the rest of the company's internet traffic.
Here's where it gets really interesting. Because voice calls are now just streams of data packets. They're ones and zeros sharing the exact same physical office network as, say, the marketing team downloading 4K videos and the accounting team pulling massive cloud databases.
Yep, it's all in the same pipe.
And if I watch a video on a congested network, it just pauses and buffers.
Mm.
I might be annoyed, but, the video eventually plays. But a live phone call cannot buffer.
No, because humans are incredibly sensitive to audio delays. We can tolerate a fuzzy video, sure, but if the audio in a live conversation degrades, communication breaks down immediately.
You just end up talking over each other.
Exactly. So we have to differentiate between two major network enemies here: latency and jitter.
Okay, let's define those.
Latency is the sheer delay. That awkward 2-second pause where you both start talking at the exact same time because the packets literally took too long to cross the ocean.
We've all been on those conference calls.
Right. But jitter is when those data packets arrive at the destination out of order. Your voice gets chopped up, scrambled, and reassembled incorrectly, resulting in that horrible robotic stutter effect.
So how does an IT architect prevent latency and jitter when someone in marketing is, like, downloading a 50-gigabyte file?
By diving deep into the networking syllabus outlined in our training sources, the network curriculums we reviewed literally structure this as a core requirement, like Module 4, Networking for PBX.
Oh, right, where they outline the exact skills needed.
Yeah, they mandate that administrators must master IP addressing, subnetting basics, router and switch basics. A modern PBX administrator has to be a highly competent network engineer.
It's not just plugging in phone cords anymore.
Far from it. They have to understand VLAN concepts to deploy something called a virtual local area network. On a specialized Layer 3 network switch, which is hardware that can actively route IP addresses, not just connect local devices, the engineer configures a dedicated voice VLAN.
Okay, so what does that actually do?
It takes the physical network cables running through the walls of your office and virtually slices them into isolated lanes. It completely segregates the SIP voice traffic from the standard HTTP web traffic right at the hardware level.
It is like painting a dedicated bus lane onto a crowded digital highway.
Precisely. The heavy data trucks can be bumper to bumper, but the voice packets fly down their own empty lane.
But wait, what if the internet connection leaving the building is the bottleneck?
That's where the next part of that Module 4 curriculum comes in. Segmentation alone isn't enough. The engineers must also deploy QoS, or quality for voice traffic.
Right, quality of service.
Yeah, QoS is a strict hierarchy of rules programmed into the router that evaluates every single packet of data leaving the building.
It essentially gives voice packets VIP treatment.
Exactly. If an email packet and a voice packet arrive at the router at the exact same microsecond, QoS forces the router to hold the email and fire the voice packet first.
That instantaneous prioritization is what keeps the dial tone pristine.
It's crucial.
But we also have to look at how that voice packet is generated in the first place, which brings up the audio codecs mentioned in the curriculum, things like G.711, G.729, and Opus.
Yeah, codecs are fascinating.
I really wanted to ask about those because my assumption was that they just compress the audio file, kind of like turning a massive WAV file into a tiny MP3.
It is much, much more sophisticated than that, especially with a codec like G.729, which is widely used to save bandwidth in enterprise systems.
So it's not just making the file smaller.
No, it doesn't just squish the audio wave. It actually uses mathematical algorithms to model the human vocal tract.
Wait, really? The physical vocal tract?
Yes. It analyzes your speech, strips out the background noise and the silences, and transmits a highly compressed mathematical instruction set. The receiving phone takes those instructions and synthesizes the sound of your voice on the other side.
That is mind-blowing. It's synthesizing my voice in real time based on math.
Yeah, and this reduces the bandwidth required by an enormous margin, allowing a congested network to handle dozens of simultaneous calls without any jitter.
That's incredible. But because all of this, the CPR trunks, the voice VLANs, the synthesized codecs, is fundamentally data traversing the public internet, the entire PBX is highly exposed.
Oh, absolutely. It's a massive target.
Which explains a very jarring quote I found in the Telecom Complete PBX manual. The product manager literally states in the training documentation, "Hackers love to target IP-based exchange systems. You should be paranoid."
When official technical documentation abandons that sterile corporate speak just to tell administrators to be paranoid, you know the threat vector is severe.
It really raises an important question. Why? I mean, I understand hackers breaching a server to steal credit cards or encrypt data for a ransomware payout. But why are they targeting the corporate phone system? Are they trying to, like, record sensitive boardroom phone calls?
I mean, corporate espionage happens, sure, but the primary motivation is actually much simpler than that. It's toll fraud.
Toll fraud?
Yeah, they want to steal money directly from the company's telecom budget.
Wait, if they hack the phone system, how does that translate into cash in the hacker's pocket? Are they just acting as digital joyriders, making free long-distance calls?
To understand the monetization, we have to examine a PBX feature called DISA. That's Direct Inward System Access.
Okay.
The sources detail how DISA is designed as a convenience tool. Imagine a company executive traveling internationally. Instead of paying exorbitant hotel phone charges or mobile roaming fees to call clients back home, they dial a specific local DISA number. They enter a PIN code, and suddenly they receive an internal dial tone from their company's PBX back in the States. From there, they dial out through the company's SIP trunks, utilizing the company's cheap outbound rates.
That sounds incredibly useful for remote teams. But you are essentially punching a hole through your own firewall and hanging a live corporate dial tone out on the public internet, protected by nothing but a PIN.
And that is exactly what the hackers automate. They write scripts that constantly scan the internet for open DSA ports or vulnerable PBX administrative logins.
Just constantly knocking on doors.
Yep. Once they find one, they launch a brute force attack, guessing thousands of pins a minute until they break in. Once inside, they have unfettered access to the company's outbound SIP trunks.
And here's where the economic model clicks into place for me. They aren't calling their friends. The hackers go out and acquire premium rate phone numbers in foreign jurisdictions.
Yeah.
Numbers that legally charge, say, $5 or $10 a minute to connect, much like the old 1-900 numbers here. The telecom providers hosting those premium numbers share the generated revenue with the owner of the number.
Who is the hacker?
The hacker.
The trap is set. The hacker configures their automated software to use your compromised PBX to dial their premium numbers thousands of times an hour. And they usually launch these attacks late on a Friday night.
Right, because the IT staff has gone home for the weekend.
Exactly. The script will just make automated calls all weekend, racking up connection charges. The hackers' premium numbers generate massive kickbacks, and by Monday morning, the corporate victim is slammed with an $80,000 international SIP trunk bill.
Toll fraud is a volume game. They are essentially laundering the company's telecom budget into their own pockets. It completely validates the manual's warning to be paranoid.
Absolutely.
If an admin doesn't lock down international routes in the dial plan or, allows users to set 1, 2, 3, 4 as the PIN, the system will just be decimated.
Securing the perimeter is paramount. But even when the network is secure and the hackers are kept at bay, IT professionals still have to maintain the system. And troubleshooting a modern PCX perfectly highlights the bizarre dual reality of current telecom engineering.
The eStar and Complete PBX manuals showcase this beautifully. They outline two entirely different troubleshooting methodologies depending on whether you are fixing a modern digital line or a legacy analog line.
Right, night and day.
If an engineer is troubleshooting a SEP trunk, where, say, a call keeps mysteriously dropping after 30 seconds, they use a tool called an Ethernet capture. They pull a raw copy of the data packets right off the network interface, export it into a protocol analyzer like Wireshark, and literally read lines of code.
Yeah, they're scanning text for SIP error messages, like a 403 forbidden or 487 request terminated. They're tracking the exact milliseconds where the negotiation failed.
They are diagnosing software communication. But when that same engineer has to troubleshoot a legacy analog FXO port like an old-school physical copper wire connecting a fax machine or an emergency elevator phone, they cannot read it like code. The data isn't packetized.
No, it's just raw electricity.
So they use a port monitor tool, and this blew my mind. The tool records the raw electrical frequencies coming across the copper wire. The engineer exports that electrical data as a W80 audio file, drops it into a sound editing program like Adobe Audition, and puts on headphones to physically listen to the problem.
It's wild.
They're listening for voltage drops, static hums, and the precise pitch of the signaling tones to figure out why the call won't connect.
It is the perfect encapsulation of the telecom industry today. Engineers have one foot firmly planted in the world of pure IP packet routing, and the other foot is still managing the physical electrical pulses that defined the last 100 years of communication.
So what does this all mean for you? We started this deep dive looking at that simple plastic hardware sitting on your desk. But to make it ring, an incredibly intricate lightning-fast dance has to execute flawlessly behind the scenes.
You have SIP endpoints rigorously registering themselves on the network. You have trunk channels hunting via strict round-robin algorithms.
You have dial plans intercepting digits, rewriting them, and forcing routes in real time.
You have layer 3 switches enforcing those voice VLANs we talked about, creating dedicated lanes for G.729 codecs that are mathematically synthesizing human speech.
While QoS protocols ruthlessly prioritize those packets over everything else to prevent jitter.
All while fending off automated brute force scripts trying to bleed the company dry through toll fraud.
And every single piece of that sequence happens in a fraction of a millisecond, every single time you lift the receiver. So the next time you are sitting on hold in a massive call center queue, listening to grainy, compressed elevator music, try not to get frustrated.
Just think about the engineering.
Exactly.
Yeah.
Take a second to appreciate the sheer volume of packet switching, pattern matching, and priority routing happening at the speed of light just to keep your connection alive.
It is a marvel of modern IT infrastructure that operates silently in the background, completely unappreciated until it breaks.
It really is. But it also leaves me with one final thought. The training manuals we explored today highlighted how completely PBX systems have merged into our software-defined networks. Orcom is even pushing AI virtual agents to handle complex IVR menus and dynamic call routing.
Oh yeah, it's all software now.
Right. So as these systems become purely data-driven and AI natural language processing handles the endpoint routing, will the concept of a standard 10-digit phone number eventually become entirely obsolete?
That's a fascinating question.
Will we soon just initiate voice packets to a data-driven user ID, completely abandoning the legacy of the dial digit? Just something for you to ponder the next time you hang up the phone.
A structural shift that is likely closer than we think.
Thanks for joining us on this deep dive. We'll see you next time.